people put the coach.
Yeah. That actually sounds.
I didn't finish.
Did you like it?
I didn't coach it.
You have to. I think that there are some may have some film in English.
Oh, maybe some websites translated.
Yeah, I think it's
Be nice.
well.
How are you?
Hanging in.
Yeah,
I'm gonna sit again, so.
I think so.
What's that?
Wish you would have.
Oh, thanks. Yeah, it's been a rough go. So.
Oh, just how you- I would love. Okay, and come sit down. Show you. Because I have to.
Thank you.
Did you say that? Transition.
Yes, very soon. I will have coaching. I have something to do. Yes.
Morning, everyone. We'll get started in a little bit here. We're still waiting on some people, so. All right, I think some people slept in, but we're gonna go ahead and get going. So, good to see everybody. Apologize if I have to like pause a little bit today, but I'm trying to give it a go here with coming into the office. So I'm about 2/3 of the way through the drafts of the full drafts of the projects. Couple general points that I want to raise, and I'll be sending comments to everybody else hopefully today. But remember that there's formatting requirements for the final project. So this is clearly laid out in the final course project document. So remember the project's got to be double spaced, not single spaced. I was reading some 15-page drafts that were single spaced. That's a lot of text for the purpose of this project. So it's double spacing, 12-point font, okay? Also, the introduction should be very brief. I was reading some 4-page lit reviews. Okay, that was not the purpose of this project. Okay, this was not a course in literature review. This was a course in analysis. So just very brief motivation and a clear statement of the objectives of what you want to do with your analysis, that suffices for the introduction. I really want to focus on your approach to the analysis, the modeling, okay, how you accounted for complex sampling features in the analysis. That should be the primary focus, okay? For the most part, people did a really nice job with tables and everything. It's okay to put some tables in supplementary materials if that's going against the page limit. Just make sure that there are clear references to those tables in the actual text itself. And remember that you do need a discussion section. So some of the drafts were missing a discussion section that kind of ties together all the results and doesn't just regurgitate the results, but rather thinks about the implications of those results for your broader research questions or the population in general. So think a little bit bigger picture about what your results mean with respect to the original question that you sought to answer, okay? Okay, so again, I'll be trying to get through the rest of those today, but if you have any questions about the comments or edits that you're receiving, just shoot me an email and we can set up a meeting or something like that. Last thing is design effects. Most people done a really good job of reporting on the design effects as a part of the analyses. Remember that you're going to be reporting design effects for each of your analyses. So descriptive analyses, regression modeling, whatever the case may be. And remember just to provide a brief interpretation of those design effects. So I was reading some statements like, you know, the complex sample increased the variance estimates by anywhere from 1.5 to 1.9 times, right? What's missing from that statement? Relative to a simple random sample of what? The same size, right? So when we're talking about variance inflation, it has to be with respect to what, right? So the sample size might be changing across the different estimates that you're computing. So you want to make it clear that this design effect is capturing variance inflation relative to what you'd see with a simple random sample of whatever size was used for that particular analysis, okay? But most of you did a good job at least mentioning the design effects. So. Okay, questions about the projects or any of those logistics moving forward? Any questions?
What's the base?
12. Yep. So Carrie, make sure to go back and review the final course project document that's up on Canvas that lays out all the guidelines for the final submission. Okay, so it's 12 double-spaced pages, 12-point font, inclusive of the figures and tables that you want to add. But you can add appendix, yep, if you wish.
Yeah, because some of the results are so big.
Yeah, that's okay. Yep. Other questions about the project? Okay. If not,
There's another question.
yes, yep.
If your regressors are, for example, are more,
Are what? Excuse me?
are like are many, if you have more regressors.
Okay.
At the first stage, so you need to know significance here. so on, then retain final step.
Yeah.
So their maximum regresses.
That's an issue of statistical power, right? So generally, a rough rule of thumb, depending on the type of model that you're fitting, is you can reliably estimate as many parameters as you have sample size divided by 15. That's a rough rule of thumb for regression models, but we haven't really covered sample size issues in this particular class. Generally, with these large national survey data sets, even if you talk about the effective sample size, you're still going to have a big enough sample to include a number of different predictors. So I wouldn't let that kind of derail what you're doing right now. Most of these data sets are large enough to accommodate a number of different predictors, but you can actually do a power analysis and see how many predictors you can reliably estimate coefficients for. But we haven't obviously talked about that in this class, so I just don't worry about that for now.
This data we can use the power analysis.
Yeah, but again, that's not the focus of this class. It would be a waste of your time to do that right now. Let's just focus on fitting the model that you want to fit, interpreting it correctly, writing it up concisely. That's the focus. Okay. Okay, other questions about the project at this point? Okay. Okay, so today we'll be talking about missing data. So many of you have had questions, comments about what to do about missing data when you're performing analysis. And we're going to talk about missing data strategies today, but also how to deal with complex sampling features when you're dealing with those missing data problems. Okay, so that's a big focus given the theme of this course is what do we do about complex sampling features when we have to deal with missing data? And clearly, given that this topic comes relatively late in the course, you don't have to worry about, all of a sudden going back to your projects and implementing everything we're talking about today and trying to fix problems with missing data. Don't worry about that. Just be clear about your sample sizes that you're actually using in the final projects. And you can say that future analysis might consider imputing missing values or something like that using the techniques that we'll discuss today. But there's absolutely no need to spend the next 2 weeks worrying about multiple imputation and things like that. This is just to give you an overview of practical approaches to dealing with item missing data in this complex sampling context. Okay, so here's an outline of what we'll be talking about today. We're going to talk about the distinction between patterns and mechanisms when it comes to missing data. Okay. We'll talk about some relatively simple methods and strategies for dealing with item missing data. Then we'll get into a discussion of what's called multiple imputation. We'll talk about different software options that are out there for implementing multiple imputation. We'll briefly talk about something called fractional imputation, which is another strategy for dealing with item missing data. And then I'll point out some references and additional reading where you can go to learn more about this. Some of you at an earlier lunch met Dr. Rod Little. He's probably the foremost living statistician who's made the most fundamental contributions to everything that we're talking about today. He and Don Rubin, both still alive, are really legends in this particular area. So if you have a chance to interact with him during the remaining 2 weeks, if you want to pick his brain about missing data problems that you or your agencies or your institutions might be having, would be very good to try to set up a meeting with him. So. Okay, so let's start with patterns. Patterns of missing data. These describe basically the distribution of the missing values that you actually observe in the data set. Okay, so literally, what cases have complete data, what cases have missing data. Okay, so a pattern concerns if we were to create an indicator variable, which is a 1 if a variable is missing and a 0 otherwise. The pattern is just what is the pattern of those 1s and 0s in the overall data set. That's all. It's a very descriptive concept. Okay, so some example patterns were in these data sets that you see here in green. The rows represent cases or respondents in the data set. The columns represent variables. These are just pictures of what the patterns might look like. So the most common one by far that you see in these big national survey data sets is this general pattern. Okay, some people call it a Swiss cheese pattern. So it looks like a block of Swiss cheese, where the missing values are seemingly just occurring at random in the entire data set. You have randomly distributed holes here and there where you didn't actually observe the variables that you wanted to observe. And some variables are completely observed for everybody. Okay, so that's something that we definitely leverage in dealing with missing data problems, is having some of our variables completely observed for all the different cases. So that's the typical pattern that you're going to see in these kinds of survey data sets. But there are also a variety of special patterns of missing data. One is a monotone pattern, where there's, again, not really a random pattern of missing values that you see haphazard, but rather there's dropout as variables move on, or in a panel study, people might drop out and not come back over time. And the sample size just gradually decreases with each additional variable that you're measuring. And that kind of monotone pattern allows for some specialized techniques that you can use to impute the missing values. Okay? But you see, there's not kind of a random Swiss cheese pattern. It's just the amount of missing data keeps going down and down. And if you have missing values on a prior variable, you're also going to have missing values on future variables. Okay? A univariate pattern, where for the most part, every variable that you observe is complete, but then you run into the occasional variable where there's just a chunk of people with missing values. This could be due to skip patterns or not applicable questions, like if you're asking males how many babies they've had, things like that, okay? Where you just have missing data on a particular variable, but there doesn't seem to be a distribution among the other variables. Then you could have file matching problems. This is where you're trying to append two data files or merge data files, and something goes wrong in that integration process, okay? The picture that you see here, you might have a variable called BMI in one data set that you're combining, and you might have a variable called BMI1 in a second data set that you're trying to combine with the first data set. Those variables have different names, so when you stack the two data files together, although you might want them to appear in a single variable, they end up showing up in different variables. And you introduce this kind of offsetting problem here in terms of missingness, where for one variable, everybody in the second data set's missing. For the next variable, everybody in the first data set's missing. And then when you try to analyze your BMI variable, you're losing half of your sample. That's something that arises from a data management problem, where you haven't done enough work to harmonize the variables that you're working with. Okay? So these are all different patterns that might emerge, and the special patterns at the bottom are unique. The more common one that you see in practice is the general pattern. So that's going to be our primary focus moving forward. Another type of missingness that you might observe, depending on the design of the survey, is something called matrix sampling. Okay? This is where everybody in the study gets asked a core set of questions. So those are those common variables that were observed for everybody. But then by design, different survey respondents get different random subsets of additional questions. Okay? So if you had 3 additional modules or something, the first random subset of cases might get the second and third modules. The second subset of cases might get the first and third modules. The third subset of cases might get the first and second modules. Okay? So that's missingness that's planned by design, and it creates this matrix kind of pattern. And so that's where this name comes from, matrix sampling. Okay? You're randomly sampling different cases to get different additional sets of content. And the fact that this is missing by design allows us to impute those missing values as a function of everything that was fully observed. So this is missingness that was planned by design, where the survey designer had full control over the missing data pattern. And that opens up the door to a number of options for recovering those values that you didn't observe by design for particular subsets of cases. Okay, so that's known as matrix sampling. That's another pattern that you might run into depending on the survey design. Okay, so patterns. Really, these summarize which values are missing. It's nothing more complicated than that. Which cases have a 1 on a missing data indicator, which cases have a 0. Okay, that's it. The mechanism is more complicated. Okay, the mechanism is not the what, the mechanism is the why. Okay? Why are the values missing on particular variables? Is it something to do with the survey variables that you are actually trying to collect in the study? Or is it a function of other observed variables, but not the variable that you were trying to observe? Or is missingness just occurring completely at random? No rhyme or reason, not a function of the variables you've observed, not a function of anything. Is it just occurring completely at random? Okay. So the mechanism says, why are you seeing missing values, as opposed to just simply what the missing values are. So the notation we're going to use in this lecture, let's say that Y is the full data matrix if no data were missing. So if you'd conducted your survey and you'd been able to observe data on everybody, you would get Y. Okay, that's the true underlying data set that if everything in the world was perfect, you would have been able to observe. Okay, that's Y. M is then a missing data indicator matrix that's laid on top of the full data set Y, where if you weren't able to observe a particular variable for a particular case, that particular case gets a 1 for that variable of interest. If you did observe the variable of interest in Y, that case gets a 0 for that variable of interest. So M is just an indicator matrix for what values were missing and what values were actually observed. All right. So patterns concern the distribution of M in general. What are the ones? What are the zeros in the overall data set? The mechanism concerns the conditional distribution of the M's given the values in Y. All right. So knowing what the true values are that you would have been able to observe if the world was perfect, okay? What's the probability of having missingness? Okay, conditioning on those values of Y. That's the mechanism. So what's the relationship of the values in Y with the probability of having a 1 on those missing data indicators? That's the mechanism. So when we talk about missing data problems, we have to clearly distinguish between patterns that are just descriptions of the missing data distribution and mechanisms, which are the conditional distributions of the indicators given the values in Y. And we're going to think about use of different methods depending on what the underlying mechanism is or what we're willing to assume about the underlying mechanism. All right, so these are the 3 most widely recognized mechanisms in the missing data literature. Okay, the first mechanism is called missing completely at random, or MCAR. Okay, this is where missingness is independent of that true data matrix Y. Okay, so the pattern of missingness has nothing at all to do with the actual values in the full data matrix Y. Okay, missingness is just occurring completely at random. It has nothing to do with the variables that you were actually trying to observe. It has nothing to do with other variables in the data set. Missingness just happens completely at random. Okay, so statistically, we would say the probability of missingness conditional on Y is simply equal to the probability of missingness. It has nothing to do with the values in Y. Okay, MCAR, as it's often abbreviated by, is the strongest assumption that you can make about a missing data pattern. Okay, you're saying that there's really no rhyme or reason to the missing data, and that the cases with complete data are a simple random sample of everybody in your original data set. Okay, that's the strongest assumption that you can make about a missing data pattern. And as we'll talk about later, MCAR is the assumption that you're making when you use listwise deletion, say in a regression analysis or in a multivariable analysis, and you just drop cases with missing data. You're assuming that you're working with a simple random sample of the full survey data set, which doesn't introduce any bias, as we know, okay? And that missingness has nothing to do with the variables that you were trying to observe. Okay? So a weaker assumption, as far as mechanisms go, is missing at random, or MAR. Okay? Missing at random means that the probability of missingness only depends on the components of that data matrix Y that you were actually able to observe. So in this case, for example, missingness might depend on the fully observed variables in the data set that you were actually able to record in the survey. Okay. Missingness doesn't depend on the values of y that you were not able to observe. Missingness depends on the value of the values of y that you were able to observe. So this is where you, if you fully observe gender, say, for an entire survey, the probability of missingness might vary for males and females or something like that. Okay. So that's a slightly weaker assumption. And making the missing at random mechanism plausible means that you're bringing in more and more fully observed variables, where once you condition on those fully observed variables, missingness is only occurring at random within the subgroups defined by those variables. Okay? So the idea of missing at random, let's say you're trying to predict missingness, and you condition on gender, race, ethnicity, age, education, and all those sociodemographics are fully observed in the data set. Okay? The mechanism that you're assuming is when you look at somebody who has the same gender, the same race, ethnicity, the same age, the same education, and you create a pool of all those people with common values on those fully observed variables, within that pool, missingness on other variables is occurring completely at random. That's the idea of missing at random. Once you condition on fully observed values on other variables, only then, within the cells defined by all those other variables, is missingness occurring completely at random. So the people with missing values on your variables of interest are a random subset of everybody within that cell, defined by the other variables. That's missing at random, okay? So in practice, we make the missing at random assumption plausible by using as many auxiliary variables as we can that were fully observed in modeling the missing data patterns. Okay, we're going to keep coming back to that idea because many popular missing data techniques make the assumption that the data are missing at random. Okay, now I ask a question at this point. Can you prove with the data set that you have in hand that a missing at random mechanism holds? Is there any way to actually test that a missing at random mechanism holds in your data set? What do people think? No, it doesn't have to do with subpopulation analysis or anything like that. No. Just thinking about Y and M. Is there any way to prove empirically that the missing at random mechanism holds? No. Right? Because we can't look at the values that we're missing to see if missingness was a function of what we were actually trying to observe on the variables of interest. They're just missing. They're in the data set. Okay, so we can't see if missingness was actually a function of the variables that we were not able to observe. We don't have them. So it's a very funny story. One of my former mentors, when I first started working in consulting, we had a very difficult client. You guys all have probably experienced very difficult clients at some point. And this client was very needy, had a lot of questions, et cetera, but this idea of missing at random was especially challenging. And he laughs, he'll laugh and laugh and laugh every day if I bring it up, about a time where he was just sitting in his office and he could hear me on the phone talking with this client who just kept asking over and over and over again, why can't I show that missing at random holds in my data set? And I was like, client, because you don't see the values that weren't observed. But why can't I show it? Because you don't see the values. But why? Because you don't see the values. And he's just sitting in his office with tears in his eyes. And this conversation went on for like a half an hour. So you can't decisively show that missing at random holds. You can show that missing completely at random does not hold by showing that missingness depends on other observed variables. That you can do. Okay, Rod developed a test for that actually. But you can't show that missing at random holds. Okay, you can only really do that in simulation studies that you manipulate. Folks on Zoom, can you mute if you don't have a question, please? George, I think you're not muted here, so thank you. Okay, Now, so that gets to the third mechanism, which is the most difficult mechanism to handle in practice, which is not missing at random, or as it's been called more recently, missing not at random, MNAR, NMAR. Not missing at random means that the probability of missing this depends on the values that you weren't able to observe. Okay? So this comes up often on variables like income, where you don't actually collect a person's income because the people with the highest incomes don't want to report them. You don't actually collect a person's weight because the people with the lowest or the highest weight don't want to report their weight, or they refuse a measurement, or whatever the case may be. And that holds even if you condition on the other fully observed variables. So even if you look in cells defined by age and education and sex and whatever else is fully observed, and those variables might be predictors of income. Even when you condition on all the other observed variables, the people who are missing values within those cells on other variables of interest are missing because of the values that you weren't able to observe. Okay? And clearly, because of that, it makes it very difficult to adjust for that kind of non-random missingness in your analysis. We're going to talk about strategies for doing that. But this missing not at random mechanism is an example of a non-ignorable mechanism when it comes to missing data adjustments. Sometimes the mechanisms are referred to as ignorable or non-ignorable. Non-ignorable means we can't get by in an analysis unless we make some assumptions and we do a sensitivity analysis. Ignorable pertains to missing completely at random and missing at random, because with enough covariate adjustment, we can implement techniques to correct the bias in those mechanisms. Okay, so first two mechanisms classified as ignorable. Third mechanism, non-ignorable, and we need more specialized techniques for dealing with that. But again, we can't conclusively show with the data in hand whether we have a MAR mechanism or an NMAR mechanism. These are assumptions that we make, and we can do our best to make the MAR mechanism more plausible in our missing data analysis by adding more covariates to the mix. Okay. So let me pause for a second. Any questions about these three mechanisms that are more widely recognized in the literature as kind of encompassing the different possible mechanisms that might be operating? Questions about these? Okay, so when we use techniques like multiple imputation, we're making the assumption that the missing at random mechanisms hold, because we can go within classes and then impute because missingness is occurring at random within those classes. We can take somebody that was observed in those classes and use those values to impute what was not actually observed, because everything's happening at random within those classes. That's kind of a building block assumption that we make moving forward. All right, so there are different alternatives for handling missing data in surveys. It's a vast literature. Okay, so we're just kind of touching the tip of the iceberg today and introducing you guys to some of these concepts, but it's a gigantic literature in statistics in general. One approach, which is what people predominantly are going to do on your final projects, and that's okay, is to conduct complete case analysis. So that is, you throw out the cases that have missing data on your variables of interest, and you just analyze the cases that are fully observed on all your variables. And this is often the case with multivariable models. This is what most software will use by default. It's called listwise deletion. Okay? So when you're doing a multivariable analysis, linear regression, logistic regression, something like that, you're deleting cases that don't have complete data from that analysis. Okay? So when you do a complete case analysis, you're making the assumption that the missing data mechanism is missing completely at random. The complete cases that you're analyzing are just a random subset of all the cases in the data set. Maria?
It's about the other slide. I want to clarify, you said that income is not missing at random.
Just using that as an example, it might be. I'm saying it's often the case where with financial questions, people with higher values tend to say, I'm not sharing that information with you.
Yeah, I know. But if I want to imputation in income, we have to assume that it's missing at the random.
Right, that's the issue. And that's why if you assume missing at random, you may still have biased estimates even after imputation. Because suppose that people who don't report their income consistently have a higher value, right? You're assuming that even within those cells conditional on all those other variables, that the people without data on income look just like the people with data, right? So if the people with data consistently have lower income and you're grabbing those values to impute the values of the people without, you're consistently undervaluing the income for the people you were imputing. That's why that mechanism can lead to bias, and assuming missing at random doesn't fix it. So you need other sensitivity analyses to do those kinds of imputations. That was another entire chapter of my dissertation, was a method for dealing with the not ignorable problem. And it always relies on sensitivity analyses. Yep. Yep, Nancy.
Just an addition. So for us, for income, we use expenditure. Imputation.
Sure. If you're willing to make the argument that expenditures explain a large fraction of the variability in income, and that when you condition on expenditures, missingness on income is occurring at random, then that would be reasonable. But if missingness on income, even after you condition on expenditures, is still depending on the values of income that you weren't able to observe, that not ignorable mechanism is still going to hold. And there could still be bias. But what you're getting at, Nancy, is the strategy that we try to use in practice. We try to find fully observed variables that are as predictive of the variables of interest as possible, so that when we condition on all those other variables, we can at least think that that missing at random assumption is plausible, because we formed a cell where everybody basically looks the same. That's what we try to do. But again, we can't show that conclusively, simply because we don't see the income values for the people who didn't provide them, right? So we have to make an assumption. Okay, so complete case analysis is, again, missing completely a random assumption. One strategy is to weight those complete cases. So adjust the survey weights for those cases that provided complete data to account for the additional cases that were dropped. It's like an additional non-response adjustment. The problem with step 2 is that you'd have to develop separate weighting adjustments for every single analysis that you want to perform. It's not a good business to be in, where you're just making up weights every other day, depending on what analysis you're doing. You could do it in theory, okay, but there's a lot of implications of doing that. Okay. A third approach, analyze the incomplete data using one of 2 techniques generally. One is the EM algorithm. It's called the expectation maximization algorithm, to try to fill in those missing values, re-maximize the likelihood, fill in those missing values again, re-maximize the likelihood. Okay, that's a strategy. Okay, just starting with the incomplete data, you don't have to do any weighting or anything like that. A related strategy is full information maximum likelihood. So you're actually using information from the cases with incomplete data to define the likelihood function. Okay, so that's another strategy that one can use, which is a reasonable one, especially for longitudinal data. Okay. Other strategies involve imputation, which we're going to be talking about today. So one could perform a single imputation of missing values. An imputation just means that you're predicting what those missing values would be in the data set. The first job that I had at the US Census Bureau, back when I was an undergraduate, the person who was going to be my supervisor said, okay, Brady, you're going to spend the summer doing editing and imputation. I had no idea what imputation was. I'd never even heard the term in a statistics course. I read that as being inputting data. I said, oh man, I'm going to go out to Washington, D.C. and I'm going to spend the whole summer entering in data. And she said, no. What you're doing is you're going to be developing models to predict what those missing values should have been. Okay, that's what we mean by imputation. And so there's a variety of methods you could use to develop predictive models for cases with missing data, and I've listed some of those here. But the difference here is whether you do that once, you predict the missing values once, or you do it multiple times. And that's the idea of multiple imputation, okay, where you acknowledge that a prediction is just that. It's something with uncertainty. And you don't assume that the one predicted value you get for a case with missing data is the truth. You repeat that prediction process multiple times, and you do multiple analyses allowing for that uncertainty to emerge. Okay, that's what we're going to talk about today. So those are other kind of, fill in the blank methods that you could use for dealing with missing data. So we're going to touch on each of these as we go. All right. So this is a picture of those general strategies that one might pursue. Okay. In the data set, you see the complete cases, then you see the incomplete cases where there are holes in this general pattern. Those are the question marks. You don't actually observe the values on those variables. Okay. Imputation, you would predict what those holes are based on models that are generally fitted based on the complete cases. So you fit a predictive model to the complete cases, you use that predictive model to fill in those missing values. Okay, so all those filled in red numbers are predictions based on some model. Okay, then you analyze that filled in data set. Okay. Complete case analysis, you either analyze the complete cases or you develop weights for those complete cases to compensate for all the cases with missing values that would otherwise be discarded. The major drawback of complete case analysis is that you're throwing away all that green stuff that was actually observed among the incomplete cases. We'd like to do something to leverage that green stuff that was observed for the incomplete cases. And that's where imputation can work, or analyzing the incomplete cases can work. So you're actually defining your likelihood function and your estimates based on everything that you can grab from those incomplete cases. That's the idea of full information maximum likelihood as another general strategy for doing missing data analyses. So there have been a ton of papers written. How does full information maximum likelihood compare to multiple imputation? When should I use one and not the other, etc.? That's largely what defines this literature. Okay, so there's a bunch of work in that particular regard. Okay, so what we're going to learn is that some of these methods apply to particular patterns of missing data. Others can be used generally with any pattern. Okay, properties of the methods will tend to vary depending on what the assumed mechanism is. And all of these methods have limitations. That's the very important thing to recognize. Rather than just assuming one of the techniques that we'll be talking about can fix up all our problems, the best strategy is to design a survey that minimizes missing data from the beginning. Okay? We're never going to get that complete why, but we want to do everything we can in practice when we're designing our survey to make the questions easy to read, to train the interviewers well, to follow up if respondents aren't sure what they're saying. Okay? Allow for probing if they're not clear how to answer a particular question. We want to do everything we can from a design perspective to minimize the missing data problem right off the bat, so that we don't have to do all this stuff and make all these assumptions after the fact. Okay? We want to nip the problem in the bud. All right, so we're going to examine the methods in detail now, but it's important to keep this in mind. We want to try to minimize the missing data problem from the get-go here. Okay, so complete case analysis, which is again typically the default in statistical packages. That's again where we throw out all the cases that have missing data on some of our variables of interest. So it's the default analysis called listwise deletion in the different packages. It's very simple, but it's very limited. And again, it relies on the assumption of missing completely at random. If missing completely at random is violated, and missing this depends on other observed variables, and those other observed variables are predictive of what you're trying to estimate, you're going to have a biased analysis by doing a complete case analysis. And that's where we want to consider some of these other methodologies to try to deal with that problem. So very simple approach, a default approach, but very limited in practice. So unweighted complete case analysis is easy because we can just simply kick out those cases and not worry about it. It doesn't make up data. So that's something it has going for it. We're just using what's there to do the analysis. With a small amount of missing data, complete case analysis may be fine. You know, if you're losing 0.5% of your sample due to item missing data, 1%, you're losing 5 cases. Throwing those cases out, not going to be a huge deal. If you're throwing out 20% of your sample, you're at higher risk of having some kind of bias. So it's important to monitor how many cases you're actually losing. But what's the quantitative definition of small? That's problematic. It depends on how many cases are incomplete. It depends on how much information is available for those incomplete cases. And it's going to vary depending on what you estimate. A simple descriptive quantity, you might have a much larger sample size than a multivariable model. Okay? So the amount of missing data that you're actually going to observe and throw out depends on the analysis that you're doing. Okay? So these are all complications with that kind of complete case analysis. All right? So when you throw out the incomplete data in a complete case analysis, you tend to increase the variance of your estimates. Okay, there's more variability in what you're trying to estimate, more sampling variability. And you introduce bias in your estimates when the complete cases differ systematically from the cases that were incomplete. Okay, so remember, complete case analysis is restricting to the cases that have complete data and goes along with the assumption that the complete cases are representative of all the cases in the entire data set, which is missing completely at random. And as we've talked about, that mechanism is often very questionable, and you can actually test whether or not it holds as a function of other observed variables. So one approach would be to weight those complete cases to compensate for the cases that were being discarded, just like we talked about for unit non-response. Okay? But that's where weighting is typically useful, is for dealing with unit non-response, okay, like an additional stage of sample selection. Here, we're talking about different rates of missingness for different variables. Okay? So the weight that you might develop could be specific to every single variable. You could develop a non-response adjusted weight for analyses involving birth weight. You could develop a non-response adjusted weight for analyses involving income. Every single variable with missing data, you could develop a different weight. But think about the problem with that from a user point of view, a data user point of view. They open up the data set. We've talked about replicate weights, but they see 500 substantive weights. We've talked about how difficult it is to think about what a single weight is. What's a data user going to do who hasn't even taken this class when they open up a data set and they see unique weights for every single variable that you measure? Right? It's overwhelming, and it begs the question, if that poor data user wants to fit a regression model, what weight do they use? Do they use the weight for the dependent variable? Do they use the weight for the first predictor, the second predictor? It's all arbitrary. Okay? So there are many problems with using weighting to try to compensate for item non-response. It really leads to a custom weight for every single unique analysis that you might be performing. So while you can do it in theory, it has many practical issues associated with it, and it's not really a reasonable strategy for dealing with this kind of item missing data. So we know it's a simple device for adjusting for non-response from these complete case analyses. Global weights give you that same weight for all variables. That's simple, but it's better to tune your adjustments for missingness to whatever you're actually doing, whatever your analysis is. So that's the drawback. There's no built-in control of variance in doing this. Remember, the higher the variability in the weights, the more variable your estimates are going to be. So if you apply additional adjustments to your existing survey weights to account for this item non-response, you're going to get more variable weights. And as we now know, the more variable your weights are, the higher your standard errors are going to be. The design effects. So you're automatically inflating your standard errors with this kind of approach. And it's much less useful when you have a lot of covariate information that could be used to inform imputation models or maximum likelihood methods, or when the pattern of missing data is not monotone. Again, when you have that general Swiss cheese pattern, much more difficult to try to develop weights for each of those variables. Okay, so not a lot of promising avenues there when we think about weights for the item missing data problems. Okay, now imputation as an alternative, again, where we're predicting the missing values for the cases that were not actually observed. Pros of this kind of approach. It will give you a complete rectangular data file. All the holes will go away, assuming that there were no obvious, like for example, you don't want to impute how many babies a male has given birth to, right? Some imputations just have to be restricted. But for all the applicable variables, you're going to get a complete rectangular file. Another big important pro of it is that it retains the observed data. So all that green stuff for the incomplete cases, we're not throwing it away. We're leveraging it to make those predictions. So that's another important feature. Another pro is that it handles the missing data once. You're not doing something different for every single analysis that you're performing. It's a general purpose technique for handling the missing data one time. And then you can proceed with your various analyses. A fourth pro is it exploits the information in the incomplete cases. So all that green information is used to make predictions for those variables with missing values. Okay, so we're leveraging the information that's available from those incomplete cases to fill in those holes. Okay? So those are all the positives of imputation. The negatives, very naive imputation methods can be very bad. And we'll talk about what some of those are. Very common example, imputing the mean for a variable, right? If I have a variable with 10% missing values, okay, I decide to take the strategy of replacing those missing values with the mean based on everybody that was actually observed for that variable. What does that mean imputation strategy do to the distribution of the variable? If I just plug in the mean for everybody who had missing data, what does that do to the distribution?
You must be variability. This extreme case,
Yeah, you're just adding a spike in the middle of that distribution, and it's going to shrink the variability of the distribution on that variable of interest, right? You're not allowing for the random variability that defines the overall distribution of that variable, okay? So it's not going to change the mean of the variable, but it's definitely going to shrink the variance, and that has implications for a bunch of other analyses. What about for estimates of relationships? What is imputing the mean on a variable due to those estimates of relationships? If we just impute a constant value on a variable of interest, ignorant of all the other variables, what's that going to do to a relationship? If I have a relationship that looks like this, what's it going to do to that relationship? It's going to make it steeper. It's going to shrink it towards zero because I'm just imputing constant values on one of the two variables involved in that relationship. Okay? So it distorts both single variable distributions and multivariable distributions. Seems reasonable, right? We're just plugging in the mean for everybody, but there are a lot of drawbacks to that kind of naive approach. Okay? It also, nobody, not even Rod, not Don Rubin, can make the argument that imputation makes up data. Okay? As a strategy, imputation invents data. Those numbers that you see in this picture here, they're predictions. They're not true values. Okay? And it would be extremely naive to assume that they're true values in the analysis that you're doing. Okay? So individual predictions do not recognize the uncertainty associated with those predictions. And that's where multiple imputation becomes so valuable, is that we recognize that these red numbers here are not true values, but rather they're the results of predictions. And we want to simulate what those predictions might look like if we repeat that process multiple times. Okay? That's where multiple imputation comes into being handy. All right, so I mentioned imputing means. The most naive strategy is to take that unconditional mean imputation approach, where suppose we just have these two variables, y1 and y2, and we don't observe values on y2 for a certain chunk of the cases. We fix that problem by just plugging in the mean of y2 based on the cases that were actually observed. Those are our imputations. A very simple imputation model. We're just imputing with an intercept-only model for y2. Okay? So that's the idea of unconditional mean imputation. Conditional mean imputation offers an advantage in that you're leveraging the information in other fully observed variables to make a prediction for those missing values, right? So we might fit a regression model to the complete cases on Y1 and Y2, where we regress Y2 on Y1 and develop a predictive equation for Y2. And then we use that predictive equation, that regression function, to predict values on Y2. But this doesn't get around my original problem with mean imputation. What happens if Y1 is an indicator of being male versus female? And everybody who is missing on Y2 is a male. We haven't left the problem. Every single imputed value is going to be the same because we're imputing with the mean based on that regression function. And if my predictor Y1 is male and everybody with a missing value on Y2 is a male, I'm just going to have a constant set of imputed values. No different from the unconditional case, right? So imputing means generally not a good strategy. Conditional is better than unconditional because, again, we're leveraging information in Y1, but everybody who has the same values on all of our predictors is still going to get the same predicted value. And that's not reflecting the variability in the overall distribution. So it's slightly better, but not the best. Okay? So as I mentioned with mean imputation, marginal distributions and associations between variables get distorted by this kind of approach. And we want to do what we can to protect the distributions of the variables in our data set. Okay? Standard errors of the estimates that we might compute from a mean imputation analysis from the filled-in data will be too small because we're understating standard deviations. We're shrinking the distributions of the observed variables. And again, we're also overstating the sample size, right? We're pretending that those mean imputations are truth. Conditional can be better than the unconditional mean, okay, because we're leveraging information and other observed variables, but both of them can be worse than complete cases, right? We might actually get biased and higher variance estimates from some kind of mean imputation approach than just taking the complete cases as they were. That's the drawback. Bad mean imputation can be very bad, to the point where you're getting worse estimates than just doing the overall complete case analysis. Okay? So there are many drawbacks to this kind of mean imputation approach that we want to try to avoid in practice. So the way to get around those drawbacks of mean imputation is not to impute means based on some kind of predictive model, but rather to impute random draws from predictive distributions for a given variable of interest. So back to our previous model. Every single imputation was a mean based on the regression function. Remember that regression function also has residuals associated with it. So there's going to be a distribution of predicted values for different cases in the data set. And when we fit a regression model, we get a full predictive distribution for one case that we might be trying to predict. So the idea of imputing draws is that instead of always imputing the mean to fill in the missing values, we take a random draw from the predictive distribution that particular model defines. So notice back in our Y2, Y1 example, our predicted values for Y2, we might fit a regression model, that's fine. Those predicted values are going to be defined by not only just the mean for one of those cases that have missing values on Y2, but the mean plus a random draw from the residual distribution. There's going to be uncertainty associated with each of these predictions. So we take our estimated residual variance, say, from our regression model. We might assume those residuals are normally distributed with a mean 0 and some variance, like we talked about for OLS regression. And we take a random draw of a residual from that distribution, we add it to our predicted mean, and that spreads out our predictions. Okay, so you see the random draws might be those red arrows in the overall predictive distribution, as opposed to always imputing the mean. Okay? What that does is it maintains the variance of the original variable based on our regression model. Instead of always just adding a spike at the mean, adding in those random draws from that predictive distribution maintains the variance of that particular variable. So this has much better statistical properties for the filled-in data than just imputing the means as they are. So we want to take random draws from the predictive distributions when we're using these kinds of model-based methods to impute the missing values. So when you impute with random draws, it does add noise, right? We're literally adding noise from the predictive distribution. So it's less efficient than imputing the means, but we want that, okay? We want to maintain the variability of the original distribution that was captured from that regression model and its residuals, okay? So we acknowledge that we're adding noise, but we're adding noise so that we match the original distribution on that variable. And we don't get any bias for estimating distributions in taking this kind of approach. Again, conditional random draws are better than unconditional draws because we're leveraging other observed variables in the data set to make those predictions. And doing that will help to preserve associations between our variables via the regression models that are used to make those predictions. Okay, we're maintaining the association between Y2 and Y1 by using that regression model. And we're also adding random noise to reflect the predictive distribution. So those are all positive things, but the standard errors based on the filled-in data set are still going to be off. The standard deviation is going to be better relative to just imputing the mean because we're allowing for that random variability. So that's a good thing, but we're still overstating our sample size by pretending that those imputed values for Y2 are truth. They're random draws, we're better respecting the variability of the distribution, but they're still invented data. We're pretending that we have the full sample size when in fact, we have to acknowledge that those are predictions. That's where multiple imputation gives us a fix, okay? We acknowledge that these are predictions with uncertainty, so we do our analysis multiple times to propagate that uncertainty in the predicted values. That's the whole point of multiple imputation. We predict based on those random draws multiple times, okay, to capture the uncertainty in those predicted values. And we don't try to pretend that we in fact have a full data set of true values. We acknowledge that some of those values are predictions with uncertainty. And that's where multiple imputation offers a fix for that particular problem. Okay. Okay, so I think this is a good point to pause. It's about 10 o'clock. Any conceptual questions thus far on what we've talked about in terms of the different methods or the ideas of imputation so far based on means or random draws? Any questions so far in the discussion? Yep.
When you talk about weighting
Yep.
methods, you give example that I can imagine in real life that you have a weight for completed case and you want to include weights in the missing.
No. Yeah, you're treating the weight just like we've been treating the weight the whole class. You're just adjusting the weights that are already there. So you have your final survey weight that you guys are all using in your projects, and you acknowledge, you say, these complete cases, I'm throwing out 10% of my data set. That adjusted weight that you would invent just accounts for the 10% that you threw out. It's another non-response adjustment. That's all it is. What I'm saying is that your complete case analysis might be very different from Gladstone's complete case analysis, right? So you might develop one weight for you. He might develop a completely different weight because he's doing a completely different analysis. That's the problem. Every analysis is going to define a new adjusted weight, but you're just using that weight just like all the other stuff we're talking about in the class. Yep. Other questions so far conceptually? Okay, so let's take a break. When we come back, we're going to talk about how to create that predictive distribution, the different techniques we can use to model. Then we'll talk about multiple imputation, some of the software, and the ideas of fractional imputation. All right, so I'll break until about 10 after.
I'll show you an example. I don't know why. What did he say?
This one, I think, because, okay, I just use the same. Because if it's me, it's 18, right now,
Yes, it's actually safe. What's the value of number?
I know, I have it.
Because I submitted another one. I have lecture.
What about this one? Here, about our data, do you want to discuss with the authors of it? Plus?
I just try to what is higher than this. So I have to select this one. Because these are selected this one. And the next.
This one.
The number is what I find what is this? Not the same, but almost the same. So last one shows this line, now and go to that one.
Go to get and choose one.
Yeah, because I am.
Basically, trying to
Yeah, I think that makes sense.
fit all the possible.
But if you round the number, it makes sense also because
How much?
I don't know if I can round.
Why would you round that? Why round?
I
I didn't round because there was
That's what round.
yeah. This is number one. No, I checked the book.
I downloaded it. You know, it's weird. Yeah.
I tried it with it. I tried another option, but I would calculate
So much time. So much.
That is
I haven't tried it.
I know, but I'm saying, I'm just saying that.
I'll show you.
This option can run this.
I automated some part of it in Excel.
The way that I like it.
Yeah.
In selecting.
Sorry, I didn't ask any question related to the project when you asked because I thought maybe we'll do it at the end.
Yeah, we can chat today, for sure, if you have specific questions.
Yeah.
Yeah, after the class, yeah.
Yeah, mine was 971, 972. Those are linked. I can share how I did it.
971, 972.
Yeah, 971,
I
972.
will see.
Those are the linked ones.
If you are correct, I will see.
Oh, I don't remember, but like we're the same.
I will see. We have to spatial J. If this is my selection, this line.
So when you run,
I have to walking until like I say it's 25. Until we get 25. No, here.
1 6
So I have to link it. Yeah, no, but this is 13. So this is a link. And now this is 39. This is not a link. So this is not my first because I only mind about the out my selection. So 36 on the link. 32 on the link. 39 is the link. 39 is the link.
Ferrari shorts.
yeah.
37 is
Like
the
mother,
link.
like son.
And 32
One day,
is the
let's
link.
record
So I can ignore everything. Yeah, I only mind about these two. So I said,
But sometimes you can go backwards, you know?
yeah, but not in this case.
Not in that case.
Yeah, in other cases, and 26 now. Let me talk to you about this because you selected this line and I select this line because they get wrong. And I don't know.
I need to do by
Excel, I used Excel also.
No, I did it twice.
Yeah, but you are rounded this too.
I don't know what. I don't know. I have no idea.
I don't like my laptop.
Só pra mim, diferente do nosso resto tudo. Don't worry. Tá bom, né?
I also like.
Eu não linkei todo o negócio, não, só linkei o que me interessava.
Você vai sentir saudade desse curso? Eu já tô sentindo saudade.
Claro que eu vou. Eu sei que
Eu
você tem
já
saudade.
tô sentindo saudade. Muito saudade. As meninas estão me chamando de amigo. Você sabe o que é bom?
Não, sei lá quem é.
Não, mas você sabe o que é bom?
Coisa do país.
Não, então. É o cara. Ele faz mulheres.
Eu sou amada, eu vou me
É só para deixar aquele tempo, sei. Mas a questão
Match to objective. Honestly, I don't understand it, but I just saw it in some exchange.
eu falei assim, eu sempre sou casada há 33 anos.
The crucial one is this one. This is solved by automatically. Then what you do is here. I'm also lazy, so I didn't put 1 by 5. This is VLOOKUP. VLOOKUP. And you just ask this. This VLOOKUP is something. So like VLOOKUP 1 by 5. Then it knows which I'm selected. I hate switching up, but there's almost a few more.
Okay, why don't we start up again?
I have the wrong random starter first.
All right. So we've talked about the idea of conditioning on other variables to create our imputations and how we're taking random draws from a predictive distribution for a variable of interest. So it's something to think about. Every time you're making a prediction of an individual value in a data set, there's going to be a predictive distribution of what those values might be, and that accounts for the uncertainty in the estimation process. Okay? So how do we go about actually creating that predictive distribution in the first place? Every single imputation method is going to assume some form of a model for the predictive distribution of the missing values. Okay, so no matter what method you're using, there's going to be some underlying value that's being used to generate predictions that are being filled in for the missing values. Okay, that model might take the form of an explicit statistical model where the predictive distribution is based on some kind of formal model, like a multivariate normal model or a linear regression model or a multinomial logit model for a variable with multiple categories or something like that. With an explicit model, the assumptions of that model are explicitly stated and you can write that model down. And so anybody working with the data can see, oh, okay, employment status was imputed with a multinomial logit model using these variables as predictors. Okay, so that's being transparent, that's being explicit about the formal statistical model used to impute those missing values. So all the assumptions of that model are made explicit. Alternatively, you could use an implicit statistical model where an algorithm is used to develop that predictive distribution. And these implicit approaches are more in line with using machine learning algorithms to develop the predictive distributions when you're making these imputations. So classification trees, recursive partitioning, neural networks, gradient boosting, hot deck imputation, all of these kinds of approaches that could be used to make predictions are based on an algorithm. Okay, so the focus is on the algorithm, and the algorithm still implies some kind of underlying model for how the imputations are being made. Okay, so in that sense, the assumptions are implicit in the algorithm that's being used to make the predictions. Okay, either way, there's an underlying model that's being used to ultimately generate that predictive distribution. Okay, so when we conduct either single or multiple imputation, we just need to be very clear about how the predictive distributions were generated in the first place. Okay, we need to be transparent about the approaches used. So a popular example of an implicit modeling procedure is the idea of hot deck imputation. Okay, so the way that the hot deck works, you classify respondents and non-respondents on a variable of interest into adjustment cells. And those adjustment cells are based on variables that have similar observed values. So like in the missing at random assumption, you might form an adjustment cell based on age, gender, education, and race ethnicity, and look at all the people who either responded to income or did not respond to income within those particular cells defined by those 4 variables. Then you impute the missing values in those cells based on random draws of respondents who shared all the same attributes. Okay? And you plug in that respondent's actual values for the cases with missing data, for a case with missing data. Okay? Those random respondents are called donors in this context. They donate the observed information to the cases with missing information. And you're doing that with respect to other people who have the exact same characteristics that you have. Okay, so you're grabbing another person who has the same age, same gender, same education, same race, ethnicity, who actually did report their income. You're taking that income and you're plugging it in to fill in the missing value for the people with the same characteristics but did not report income. Okay, that's
Great, this is very interesting, but could it be done when some not important or not related variable with the missing value is not important? You have to match everything, or you could just look for a group of variables and do the imputation.
Yeah, ideally you want to form these hot deck imputation cells based on strong predictors of the variable that you're trying to impute. That's again to kind of like Nancy was saying, one of the variables that you might use to form the cells as expenditures, because that should have a pretty strong relationship with income. But a variable like gender or something else that might have nothing at all to do with income may not be useful for these purposes.
Yeah. So you could do that.
Yeah, you could do that, but this is the same as any kind of model. You want to identify the best possible predictors for that process. Yep. So again, this is an algorithm. You're forming cells, you're taking a random donor from within the cell to replace the values for somebody with missing data. The model implied by this approach is that you're regressing the variables with missing data on all of the variables that form the cells, including their interactions, right? It's the same implicit model as fitting a model that has all the interactions between these cells, all the cross classes. And you're making predictions based on that kind of model when doing that. So that's what I'm saying. There, you can write down what the model would look like based on the algorithm that you're using in these cases. And the same goes for machine learning algorithms and so forth that might be used to develop these predictions. Okay. So hot deck, cold deck, these are different styles of doing imputation, but the hot deck is still very popular and used by a variety of government agencies in the US to get rid of missing data problems. Okay, so this is just another kind of visual example of what's happening here with the hot deck. So you have the observed data set on the left-hand side, and notice that the 6th case is missing on X3, and the 4th case is missing on X4. Okay, so let's suppose that X1, X2, X3, and X4 all have some kind of multivariate relationship, so they're somewhat related to each other. So if we wanted to fill in that missing value on X3, we would look at other similar cases with the same values on the other observed variables. So notice that the first case in the data set also has a value of 0 on X1, also has a value of 3 on X2, also has a value of 2 on X4. Okay, so that's a case that in theory looks quite similar to the case with a missing value on X3. So that case becomes a donor, and it donates that value of 8 to the 6th case with missing data. Okay, so we're using actual observed data for other people with similar characteristics to make the imputations. Okay. Same thing for the missing case on X4. That last case in the data set has a value of 0 on X1, 4 on X2, 6 on X3. So you find another case with those matching characteristics. In theory, you take one of those cases at random and you plug in that value to fill in the missing value for that particular case. Okay, that gives you a filled in data set, but same idea, that 8 and that 2, those are predictions based on the algorithm. You might find somebody else who has a value of 0, 4, and 6 on the first 3 variables, who has a value of 3, okay, on X4, right? So if you were to repeat the hot deck process again, that filled in value would look different. That's the uncertainty that we want to account for in this kind of process. Okay? Everybody clear on the way the hot deck is working? This is just one example of an algorithm that could be used to impute these missing values. Okay? So the current population survey here in the US still uses a form of hot deck imputation. In the case of the CPS, the missing values typically occur on variables that capture earnings. Okay, income, how much you've earned from stocks, mutual funds, things of that sort. Fully observed variables in the CPS tend to be sociodemographics, like age, race, sex, family status, children, marital status, occupation, etc. All the variables that you see listed here. So in theory, you could use those fully observed X variables to form your hot deck cells. But if you think about all the possible cross classes of those variables, some of them have 5 categories, some of them have 10 categories, etc., forms a giant multidimensional matrix. Okay? And in some of the cells that result, you might not have enough sample to find donors, or there might be only 2 cases in one of those cells. So when you do hot decking, not only are you looking for good predictors of the variables with missing values, but you're trying to find some kind of definition of the cells where you have enough sample. in each of the cells. So you might coarsen or collapse the different cells in this cross classification to get to the point where not everything is based on the full cross classification, but you still have enough sample within cells that are good enough predictors of the variables with missing values. Okay, so this is not, a 30-second process to do this kind of hot decking. This takes several weeks to arrive at this kind of solution. Okay, but this is the basic process that gets followed here. Okay, so this kind of hot deck, positive features, it does impute real values. We're not making up data. We're grabbing actual observed values from other cases with similar characteristics. We're preserving multivariate associations because we're grabbing those real values that have associations with the same set of variables that we're using to do the matching. Okay? We're conditioning on the other observed X variables. So it's a conditional form of imputation. And over the years, a variety of empirical simulation studies have suggested that hot decking can work quite well when it's done carefully and it's done properly. Okay? But it's not perfect. Bad features, there could be very good statistical models of earnings that are not being leveraged here. So if you look into the economics literature, you might find better, simpler models than the general hot deck approach that could be used for the imputations. In the hot deck, we are including higher order interactions at the expense of what could be better main effects or predictors of the individual X's. So hot decking, again, implies all these interactions between the variables that are being used, and the interactions may not be important. It may just be the main effects. Furthermore, this is just done once, the way I illustrated it. So imputation uncertainty is not being included in the standard errors. Sorry, ow, it's rehearsed a cough. So when you're doing this, we still would have to do it multiple times. Okay, so just hot decking once doesn't fix the problem because, again, we would be treating these values just once as if they're true values, the analysis. And we want to try to reflect that uncertainty in what we're doing. So there's an older paper here that's referenced that talks about kind of the origins of the hot deck and how they use it. But again, they're still using a variation of this to do their imputations in that particular server. So just to summarize, when we talk about imputation, imputation should condition on other observed variables so that we're preserving the relationships among the variables. Imputation should be multivariate to make sure that we're preserving associations between the missing variables. We never want to do kind of one variable at a time imputation, okay, just plug in means. And imputation should generally be draws rather than means. So we should take random draws from the predicted distributions rather than just always plugging in the mean. And most of the software that we'll talk about now does that. Okay, so this is not something that you have to worry about if you're imputing missing values. The software is programmed to do that, but this is just iterating the concepts. The key problem with doing imputation just once is that single imputations do not account for the imputation uncertainty when your standard errors are being computed. Okay, so standard errors would be understated if we were to just do this once and assume that those values were in fact true values. So we need a solution to get around that point that single imputation doesn't give us the correct estimates of the standard errors. Okay, so if we go back to our mechanisms, these are a variety of different possible assumptions that might, or different strategies that you could use to deal with missing data. And these are some of the assumptions that are being made associated with each of these approaches. So complete case analysis, that's what CCA stands for. You see across the board, whether it's a mean, a regression coefficient, a correlation coefficient, all those analyses are assuming MCAR. Okay, so if MCAR holds for your data set, that's fine. But in general, the standard errors are going to be too large in those cases. Okay, your variances are going to be inflated by throwing out the cases with incomplete data. Okay. Using available case analysis, like full information maximum likelihood, using all observations in the data set, also can assume missing completely at random, but whether or not the standard errors are too large or too small is complicated. Depends on the models that are being used in a particular application. Mean imputation also assumes missing completely at random. We're not conditioning on other observed variables with that kind of approach. Okay? Hot decking assumes missing at random. Okay, so in hot decking, again, we're assuming that the other variables that we're conditioning on to form the cells for adjustment, those variables, once you condition on them, the cases with missing data are only occurring at random. Okay, the cases with missing data are a simple random sample of the cases within a cell that were otherwise sampled. Okay. Regression imputation also assumes missing at random. Stochastic imputation, the idea of predicting based on random draws, also assumes missing at random. So you can see all these different approaches, none of them apply to the not missing at random case. That's the point being made here. Okay. All of these different methods that could be used for imputation either assume MCAR or missing at random. And throughout, the standard errors are too small. If we just do imputation once based on these different methods. LOCF is last observation carried forward. That's sometimes done in longitudinal studies, where if a case doesn't respond in a follow-up wave, you just take their data from the last wave and you bring it forward. There's all kinds of issues with that particular approach. It's not based on any kinds of assumptions. It's just an arbitrary procedure. Okay? So that's another possible strategy. But all these methods, again, none of them allow for not missing at random or not ignorable. So how do we deal with this problem with the standard errors where even despite these assumptions, the standard errors need to reflect that imputation uncertainty? So we don't want to treat imputed values as truth. That's the biggest piece here when we do our analysis. So when we want to make inference, when we're calculating standard errors, p-values, confidence intervals, etc., we need to make sure that the methods that we're using to impute the missing values account for that imputation error. Okay, we want to account for the uncertainty in doing the actual imputations. So there are three general strategies that have emerged in the literature for doing this. One is called bootstrap imputation. Okay, so the idea there, you take a bootstrap sample of your observed data, so with replacement sample of the same size as your observed data. You develop an imputation model based on the complete cases in that bootstrap sample. Then you make the predictions for the cases with incomplete data. Then you draw a second bootstrap sample, okay, with replacement, same size, fit the imputation model to the complete cases. It's going to look different. In every bootstrap sample, you're going to have a different model, a different predictive model that would be used to make the imputations. Impute your missing values, draw a third bootstrap sample, fit the predictive model, impute the missing values, so forth and so on. Do that hundreds of times. Each of those bootstrap samples, do your analysis, calculate the estimate from each sample, and look at the distribution of the estimates. Okay? That's the idea of inference that propagates the uncertainty in the imputation model. Each bootstrap sample, you're going to get a different model. Each bootstrap sample, you're going to get different predictions for the same case. Okay? You're recognizing the overall uncertainty in the process. Okay? It just requires a lot of computation. Right? If you have 200 bootstrap samples or whatever the case may be. Okay? Another strategy that we'll talk about now is multiple imputation. Okay, so you fit a predictive model to the complete cases, and then you take random draws from that predictive distribution multiple times for the cases with missing data. So you repeat those random draws for the same case, and you create multiple complete data sets. You do your analysis for each complete data set, combine the results. We'll talk about how to do that. That's another way to propagate that uncertainty. And then fractional imputation. We're going to touch on fractional imputation at the end of the day today. But in fractional imputation, you take cases with fully observed data and you take cases with incomplete data and you divide those cases up into multiple fractions of a given case and you split their survey weights across the multiple fractions. And then you impute the missing values for each of those new multiple cases. So if I'm a missing value on income and I have a weight of 100, I might split that case into 5 new cases. And each of those cases gets a weight of 20, right? So my five new cases still sum to the same weight, an overall weight of 100, but I have 5 different cases in the data set, right? And when I use my imputation model, each of those 5 split cases is going to get a different prediction on the variable of interest because I'm taking random draws. So instead of always getting the same thing for one case, I'm getting different predictions for the same case, and I'm splitting the weight across those different cases. Then I do my analysis of that longer data set that emerges. That's the idea of fractional imputation. The common theme in all three of these methods is allowing for and recognizing the uncertainty in the predictive modeling, whether it's by bootstrapping or taking multiple random draws or splitting a non-respondent into multiple cases in the data set and calculating different predicted values for each of those cases. All of them have the same theme in terms of performance, and then they have different drawbacks and limitations that we'll talk about. But these are the commonly accepted approaches when you're doing imputation to propagate the imputation uncertainty. All right. So when we think about multiple imputation, this is the idea. Okay. You have your original data set, and the question marks represent holes following that general pattern. Okay. You fit some type of model or develop an algorithm based on the observed data that you see there, the X1, the X2, and the X3. So it might be a regression model based on the fully observed cases on X1, X2, and X3. Once you have that predictive model, you take random draws from that predictive distribution, but you don't just do that once. Every one of the asterisks here in the different imputed data sets is a different random draw. So if we look at this first asterisk here, it might be 1, then it might be 1.3, then it might be 0.98, then it might be 1.5. These are all different random draws from that predictive distribution for that case. Each random draw then gives you a complete data set. So once you have that complete data set, you can do whatever analysis you want to do for the complete data, and that generates some parameter of interest. Here we generally call it theta. Okay, theta 1, theta 2, theta 3, theta 4. Theta could be a regression coefficient. It could be an odds ratio. It doesn't matter. It's whatever analysis you want to do. Each of those data sets is going to generate an estimate of that parameter. Multiple imputation is Bayesian in nature. Okay? So we think of these different estimates as random draws of these estimates from some posterior distribution for whatever that parameter is. Okay? So we take multiple draws of these estimates from this process, and we base our inference about that parameter on these multiple draws. If that's the whole idea of multiple imputation. And that inference recognizes the between imputation variability in those imputed values, because each of these estimates is going to be different. All of these, if this is an odds ratio, my odds ratio might be 1.56 here, it might be 1.73 here, it might be 1.64 here, it might be 1.52 here. These are simulating different draws of what that parameter would look like from a hypothetical posterior distribution based on these imputed values. Okay? That's the idea of multiple imputation. Then we take all those estimates and we put them together into a single set of estimates that we're going to report for inference. We're going to see an example of how to do this with some real data here in a second. But that's how multiple imputation works. Single imputation, you would just have one of these data sets here. That's it. You generate one data, you make all your inference based on that one data, but then you don't get the variability in the data. That's the key here. Multiple imputation allows us to calculate the variability in our estimates from this process. Okay. Yep, Kier.
Sorry, Professor, I got confused with the difference with the bootstrap imputation.
Yep.
It's like I thought that bootstrap imputation we also get estimates for every bootstrap.
You do. It's extremely similar in theory. In multiple imputation, these observed values in the cases are always identical, right? These are the same cases in every data set. In a bootstrap imputation approach, the order of the data set would be different, the cases would be different, everything's different. That's the difference here. Okay, so again, we're going to see more pictures of this idea coming up here. So, advantages of the multiple imputation approach, abbreviated here by MI. It's model-based. Okay, so there's always an implicit model or an explicit model for actually calculating the predicted values, so it's transparent. It's stochastic, so it relies on random draws from the predicted distribution, And it also takes random draws of the parameters that you're trying to estimate, because we're computing those parameters for each complete data set. It's multivariate, so it preserves distributions between variables. It employs repetitions to estimate the uncertainty associated with the imputation process. It's fairly robust against minor departures from assumptions. So even if you get the imputation model wrong in some sense, like the approach still works well in terms of your overall estimates. And it's also very usable. So when doing multiple imputation, you can give a data analyst multiple data sets and say, just run your analysis of interest on each of these data sets. And modern software can then pool the results of all those estimates into a single set of estimates for inference. So modern software makes it very easy to manage and work with multiple imputed data sets. So it's not a big hurdle to give a data user 5, 10, 15 different imputed data sets, depending on how many multiples you generate. Okay, and then the user can just run their analysis using existing software and combine all the results. And I'll talk about software that can do that. Now, when you're doing this kind of multiple imputation analysis, there's a fundamental thing that you really need to be aware of. The analysis model of interest should be a subset of all the variables used in the imputation model. Okay? So a common question is, well, why would I include my dependent variable in the imputation model? Isn't that cheating? Right? I'm just imputing values of my dependent variable, and then I'm turning around and I'm fitting a model to that dependent variable. Isn't that cheating or biasing in the direction of the imputation model? We have to get rid of the distinction between dependent and independent in these kinds of imputation analyses. We're just trying to complete the data set, okay, fill in the missing values. If we were to fail to include a key analysis variable in our imputation model, we're going to get a biased estimate of relationships involving that variable in our actual analysis, because the imputation will not have recognized that part of the multivariate associations. So every single variable in the analysis model needs to be included in the imputation model. And then the imputation model can include other variables as well that might be auxiliary but still helpful for the overall imputation. So if we were to leave the dependent variable out of the imputation model, we're automatically biasing all the estimates of our relationships in the analysis model of interest. So you always want to be completely inclusive of every variable in your analysis in the model that you're using for imputation, not the other way around. Okay, so this picture just says that every variable involved in the analysis needs to be included at a minimum in the imputation model when you're thinking about what goes into the imputation model. All right, so in that imputation model, you want to include all your key analysis variables. Let's say the dependent was Y1, the independent was Y2. You want to also include other variables that might be correlated with missingness or the analysis variables, and that might be Y3 or what we're calling Z here. Okay? These are kind of helper variables that will improve the predictive power of the imputation models, but might not necessarily be part of your analysis. So that could be, for example, cluster codes or stratum codes or survey weights. Those can be included as these auxiliary variables in the imputation models to try to improve your predictive power. But at a bare minimum, every variable that you want to include in your analysis needs to be part of that imputation model. Okay. Other strategies now for dealing with the complex sample design features in the imputation model. Steve and Pat have written a nice summary of multiple imputation procedures using the SAS software. So they wrote a nice little SAS guide for those of you who are SAS users about doing this. And they talk about different strategies for incorporating the complex sample design features. Don Rubin wrote a paper talking about kind of minimal guidance about what to do here. Major, and this is a direct verbatim quote from that paper, at a minimum, major clustering and stratification indicators and sample design weights or adjusted design weights based on propensity score adjustment or whatever should be included in the imputation models. This is additional auxiliary information that could improve the predictive power of the imputation models. And that's what Rubin's saying, right? For some of our key variables, we assume that the strata vary. in terms of values on that key variable. Why not include stratum as a predictor in your imputation models? That's the basic rationale here. It may not be a key predictor in your analysis variable of interest, but for the purpose of imputing, clearly it could be an important predictor for some of your key variables. Okay. The possible loss precision when including unimportant predictors, kind of back to Gladstone's question, in the imputation model is usually a small price to pay for the general validity of the resultant multiply imputed database. Okay, so direct recommendation from that paper about using this kind of strategy. More recently, Jerry Reiter and Raghu have talked about the importance of incorporating these design features in this kind of analysis, again, using clustering indicators and stratum indicators in the imputation model itself. And then a recent PhD student, graduate from the program in survey data and data science, Hanji Zhu, who's now at Mathematica, she wrote a series of 3 papers for her dissertation, all about the idea of uncomplexing a complex sample design for the sake of making imputation. So what that means is you take the weights, the stratum codes, and the cluster codes in the existing survey data set, and you simulate what the population would look like based on those weights. You create what are called synthetic populations. Okay? And part of that synthetic population process is simulating missingness based on what you saw in the survey data set. Then, once you have that bigger synthetic population with all of its holes, you fit your imputation model to that synthetic population, okay? Generate your imputations and repeat that for each of multiple synthetic populations. But you don't have to do anything special in those analyses because you've simulated a population. You can treat it like a simple random sample. You don't have to worry about the weights, stratum codes, the cluster codes, etc. Just use your imputation model in that synthetic population without worrying about these design features. And then all of your analysis is based on those simulated synthetic populations. The same idea is used nowadays for creating synthetic data. You might have heard that term before. But that's what Hanji said. Maybe there are better ways to deal with these design features when you do the imputation. So the IVE-ware software actually makes it possible to do that synthetic population imputation using the BB design module. Okay, so that's something that's now built into IVE-ware as a way of dealing with these complex sampling features in the imputation. So there are different ways you can go. Just including the design features in the imputation models is a simple one. Creating these synthetic populations based on the design features is another one that you could use. It simplifies the actual imputation modeling. Okay. But either way, the general recommendation is that these key design variables that we've been talking about in the course should be used in one form or another in these imputation processes. Okay, so don't forget about them when you're doing the imputations. Okay, that's the recommendation. All right, so let's go back. Once we have our imputation model, the way that multiple imputation works. Suppose that we decide to create 5 imputations. And Raghu and some others have done some work saying that there aren't huge gains in efficiency by having 10, 15, 20, 5 generally suffices for the number of imputed data sets to create. So let's just assume that we're creating 5 data sets. You use your imputation model, you take your random draws, you create those imputed values, you create that many data sets that are complete now, filled in. You analyze each completed data set, okay, whatever the analysis is that you want to do, logistic regression, linear regression, Poisson regression, whatever your analysis is, perform it for each of the complete data sets. So you're going to get 5 different sets of estimates. Okay, it could be model coefficients, could be proportions, whatever it is that you're doing. Okay, you're getting 5 separate sets of estimates. You put those estimates together into a single overall set of estimates and standard errors for those estimates. And that's what you ultimately report in terms of your overall analysis results. That's called multiple imputation inference. I'm going to show you the formulas for how to do that. Okay, and again, software will do that pooling for you when you have 5 or 10 or 15 or however many it is imputed data sets. Existing software will do that for you. And we're going to see how to do that on Friday in lab. Okay, looking at some examples of multiple imputation software. So this is really useful for public use data sets because the data provider can create these imputations using their knowledge of the best possible imputation models, create these multiple data sets, and then say, okay, here users, here are complete data sets where you don't have to worry about missing this. Just make sure to run your analysis on each of them and then use these software procedures to combine the results. Okay? That's the idea. All right. So the way this combining works, these combining ideas are sometimes referred to as Rubin's combining rules because they were originally proposed by Don Rubin in a Bayesian framework back in the late 1970s. Okay. So the way this works, let's suppose that theta is our parameter of interest. Okay. So again, theta could be an odds ratio, a regression coefficient, even a simple proportion. It's whatever it is that we're trying to estimate. Okay, that's theta. Theta hat sub L is then the estimate from the Lth completed data set from the multiple imputation process. So we compute an estimate of theta from that Lth completed data set after we filled in all the missing values, after we've imputed the missing values. So we're going to get a set of theta hat L's. And then U sub L is the estimate of the variance of theta hat sub L from that Lth analysis. So if we're doing a design-based analysis, we're going to get a linearized standard error of that weighted estimate from the Lth data set. And we're going to save that. We're going to set it aside. Okay. The final combined multiple imputation estimate of theta is quite simply the average of the theta hat sub L's across the capital M completed data sets. If we have 5 estimates of a proportion, we're just taking the average of those 5 estimates. That's our final point estimate based on the multiple imputation process. This is a Bayesian idea. Think of it as being like the posterior mean of all the draws of this particular parameter. Okay. Now, here's where the variance of that final point estimate accounts for the imputation uncertainty. The MI estimate of the variance is a combination of the within imputation variance and the between imputation variance. Okay? The within imputation variance is just the average across the 5 data sets of the standard error squared, the variances of our estimates. We're literally just calculating the average variance of that estimate across the 5 analyses. Okay, that's the U bar piece of the overall variance. The between imputation variance piece, that's what captures the uncertainty between the imputed data sets in terms of what it is that we're trying to estimate. So the between imputation variance is the variability of those point estimates across the 5 data sets around the overall pooled estimate, that theta bar. Okay. That formula that you see there for B, nothing more than a formula for a variance. We're just calculating the variance of those estimates from each of the imputed data sets. Okay. And then the final multiple imputation estimate of the variance is that within imputation variance piece plus a slightly scaled version based on the number of imputations of the between imputation variance piece. Within uncertainty and between uncertainty. So we're accounting for the standard errors of each individual estimate, and we're accounting for the variability in the estimates that reflects the between imputation uncertainty in our predicted values. Okay? That gives us the overall variance. We would just take the square root of that to get our final standard error for a given estimate. So again, this is called Rubin's combining rules. You'll often hear that term when talking about a multiple imputation context, and the software is going to be displaying theta bar and the square root of V at the end of a multiple imputation analysis that reflects all the sources of uncertainty in this process. Okay. So here's an example of what this looks like using some real numbers. Let's suppose we have a data set where there are 5 variables. Okay. The middle 3 variables, Y2, Y3, and Y4, all had holes following a general pattern. Okay. So using the complete cases in this data set, we develop a predictive model and we impute the missing values on Y2, Y3, and Y4. Okay. So for the first imputed data set, these are the actual predicted values for those 4 missing values. A value of 24 on Y2, 2.1 and 4.5 on Y3, and then a value of 1 on Y4. Okay. Now, the overall analysis is interested in 2 quantities. The mean on Y1 That's one focus. And then in a regression of Y5 on the other 4 variables, the coefficient for Y3. That's what that complicated notation means there, that Rod Little likes to use this notation. It's kind of funky, but it says where 5 is the dependent variable, this is the coefficient for 3 in a regression of 5 on 1, 2, 3, and 4. Okay, so it's the regression coefficient for Y3 as a predictor of Y5, right? Those are the 2 quantities that the analyst is interested in. Now, there's no missing data on Y1, right? That's the first thing to observe. We're never imputing anything on Y1, okay? But there are missing values on Y2, Y3, and Y4, especially since we're interested in the coefficient for Y3 as a predictor of Y5. We're going to see what happens to these estimates across replications of the process. So based on this first imputed data set, the estimated mean of Y1 is 12.6. The estimated standard error is 3.6. Okay. Based on the first imputed data set, the regression coefficient for Y3 is estimated to be 4.32 with a standard error of 1.95. Okay. Now we go back and we generate a second set of random draws of these missing values. Okay. So this is the second completed data set. Different values predicted for each of those holes in the data set. Estimated mean on Y1, identical. No missing values, same mean, same variance. Okay, nothing changes there. But the estimated regression coefficient for Y3 changes because we have a different set of random draws for those predicted values on Y3 and Y2 and Y4. Okay, now the estimate's 4.15. Now the standard error is 2.64. Okay, we do it again. Same mean, okay, different set of imputed values, different random draws from the predicted distribution, same mean on Y1, same standard error, different estimate of that coefficient, okay, different standard error. So you're seeing the uncertainty in the predicted values reflected in the estimates that we're trying to compute. And multiple imputation captures that between imputation variability in the estimates that we're ultimately interested in. Here you see that regression coefficient is already varying between 4.15 and 4.86. Okay? We do it again, 4th time. We do it again, a 5th time. Okay? Each time, the estimate of that regression coefficient is going to change, reflecting that uncertainty. Then we apply Rubin's combining rules. Okay? Average estimate of the mean for Y1, 12.6. Average variance, 3.6 squared. Between imputation variance, 0. Because there was no missingness on Y1. Okay? What about our regression coefficient of interest? Average coefficient estimate, 4.36. Average variance, 2.27 squared. Between imputation variance, 0.339. That 0.339 is the whole point of multiple imputation. That's picking up the uncertainty in the predicted values that we're making to impute those missing quantities. Okay? That's the whole point of going through all this mess, is to capture that between imputation variance. And that between imputation variance gives us a sense of how good those predictions were of those variables of missing data, right? If we got really good imputation models, there's going to be very little variability in those predicted values of the missing variables, okay? And that between imputation variance is going to be small. If we have a terrible imputation model, like Gladstone was saying, we have an incorrect predictor or we leave out a key predictor, and those predicted values of the missingness all over the map, that between imputation variance, huge, okay? That's where the quality of our imputations and the information in the available cases is being picked up. Okay? So putting all this together, and this is again what the software would output, you're going to get that theta bar, which is the overall point estimate for each of those parameters, the mean of Y1 and the regression coefficient for Y3. And then you're going to get the square root of that total multiple imputation variance V, which is 3.6 for the mean and 2.36 for the regression coefficient. Okay? Another quantity that's also often computed to summarize the multiple imputation process is called the fraction of missing information, the FMI. And this is a quantity that simply reflects what fraction of the total multiple imputation variance, that's what's in the denominator, what fraction of the total multiple imputation variance is due to the between imputation variance. How much of that total variance is coming from the uncertainty in the imputed values, more or less. Okay? Many have argued, including James, in a 2010 paper, that the fraction of missing information should replace the response rate as a measure of data quality in surveys. Why? Because this is telling us if we have a very good imputation model, we can recover the information in the cases with missing data at a much better pace than throwing them out entirely, okay, assuming that they're just lost in calculating our response rate. So dealing with our sample sizes. And the ability to do that is captured, like I said, in the between imputation variance, the B term. The smaller that B term, the less uncertainty in our imputed values, the more information we have, we're able to recover. So some folks will take the response rate, if you will, after throwing out cases with missing data and compare it to the fraction of missing information and see if that fraction of missing information is lower than the actual response rate. Okay, so in this example, that fraction of missing information is about 0.07. Okay, the response rate, what was it? If we had thrown out those 3 cases, let's suppose there are 5 cases in the data set, what would our response rate have been for generating these estimates? We had 2 complete cases out of 5. What's the response rate? Just 40%, right? 2 out of 5, 0.4. Not a trick question, right? So our response rate would have been 0.4. No, that's kind of weak. Fraction of missing information, only 0.07. So we were able to recover a lot of information from those incomplete cases through the multiple imputation process. So you'll often see this FMI reported along with the multiple imputation results. And it's a good comparator with the overall response rate. Okay. So let me pause for a second. Any questions about the combining rules here or how these overall estimates are being computed? Israel?
Professor, I have a question related to the imputation about, for example, in the real life, in the real application, I imputed already a data 4 times using mice for predicting the return on assets for Egyptian banks and to compare it with Chinese banks. And when I used the method of mice and I used dynamic banner data model using GMM, all of the time, the results not logic anymore. So I used another method like latent class using for multiple imputation, which presented by Verment et al. So after using it, the results is logic. And for Chinese data, I deal with missing data using another method, which is simple imputation, single imputation only. And the results coming to be more relevant and give me it works perfectly, and I mean by that we have a good criteria that matches with the literature and its logic. Because I don't prefer to make something like, because maybe another maybe already the method using mice is nice and it's correct rather than the other method. So I mean, how can I judge for the accuracy for the imputed data? Because in the practical life, the matter is different.
Yeah, so the big judge of that is looking at diagnostics for the imputation models, kind of like you're saying. So every imputation model used has to go through the same diagnostic process that you would use for a model that you're fitting to substantive data. A lot of people treat multiple imputation like a black box. And you can't do that because if the imputation models are incorrect or they're leaving out important terms or whatever the case may be, you may get the situation that you're describing where the imputed values and the resulting multiple imputation estimates don't seem like they make any sense. So if those underlying multiple imputation models are incorrect in some way and they've not been carefully diagnosed, like for example, you're using linear regression to impute values on a binary variable, you could get very unusual multiple imputation results. So Some of the software, like the software we'll talk about on Friday, lets you go into diagnostics for each of the imputation models and make sure that the underlying models used to predict the missing values make good sense in the first place. Whatever that particular approach was, you have to make sure that all those diagnostics looks good. You're getting good predictions out of that imputation process. Otherwise, it's a garbage in, garbage out scenario. Just because you're pooling multiple analyses in this case, if each of those analyses is based on a terrible imputation model, you're going to have a poor overall estimate. Okay, so that's the critical thing to look at, is carefully considering model diagnostics for each of the models being used to look at the imputations.
Can I ask one more question? For the case that you presented in slide, I think 3, the case of for 2 variables not jointly observed in only one data set with the concatenated, like matching method. How can I judge about the mechanism here? We can say that it's missing completely at random by design.
No, that, I mean, it totally depends on the features of the 2 data sets that are being appended, right? Are they basically similar in appearance to each other, or, you know, is one data set predominantly males, or is there something unique about the data sets being added? That mechanism entirely depends on, you know, in the mismatched files, were those 2 data sets somehow different from each other in some way? So you have to look at what you know about those 2 data sets and understand the nature of the mechanism via the differences between the data sets. Yep. Okay, I know we're a little bit over, so I just want to go through some quick summaries here, real quick. Yeah, question. Yeah.
There is any golden rule to the estimated factor of this information.
Yep.
There is a golden rule.
No, there's no magic number.
No.
It's smart for a given variable or a given analysis. Compare that fraction of missing information to the response rate. So for example, if in this regression model where I was estimating this beta 3, if the complete case analysis was throwing out, again, 10% of the cases, my non-response rate would be 0.1, okay? If the fraction of missing information is less than the response rate, that says I'm picking up some useful information from the cases that were actually observed, right? It's not just that I'm throwing out 10% of the cases, I'm really losing about 7% of the cases based on this fraction of missing information. So there's not a magic number that says if it's below 0.2, it's good. It's all relative to other indicators of the amount of information available. The response rate is one indicator, right? This is a different one. So if this number is less than the response rate, it tells you that you're picking up useful information from those incomplete cases via the multiple imputation process. So it's a relative idea. Yep, Isaac.
Actually, in the real life, we are dealing with software data set, and we are dealing with the data set for the children, like nutrition or something like this. So if we are having a missing data of the children of stunting or underweight, if we don't have in the survey, so what we do, we discard or delete such kind of cases from the data set. But this is a method I have to say that we can do multiple imputation for this data. It's like
Certainly.
Or like I'm just confusing between we have like one data set, but we are dealing, or we can prepare 5 data sets or multiple data sets for multiple implications. Either we are dealing with the one data set and cutting it to the pieces, or we are
No, you're literally creating 5 data sets or 10 or however many imputations you're doing. So out of the one, right? Just like this picture. Remember, you would be providing the user with copies of the complete data set, and they would run their analysis on each of those copies.
So what is the like? We are comparing our final results with the small strip.
No, you're basing your final results on this, the combining across the data sets. So you can look at the estimates in each data set, but your final results are based on these combined estimates.
And then this is our the final tool we have compared the whole analysis like 0.07.
That's the fraction of missing information. The final point estimates would be here. Yeah. That's the theta bar. So that's your average mean, and that's your average regression coefficient. Okay, so this is just summarizing. We're accounting for the uncertainty in the imputation process. A popular way of generating these imputations is this fully conditional specification or imputation by chained equations. So Isra mentioned mice in R. That means multiple imputation by chained equations. That means you're fitting a regression model to each unique variable, and then you're making your predictions based on those individual models for every variable with missing data. And you could use a different modeling approach for every variable with missing data. Okay, so sequential regression, fully conditional specification, ICE, those are all terms for the same thing. Okay, where you're predicting missing values one variable at a time, leveraging other observed variables to preserve the associations between the variables. Okay, so we've talked about the major advantages and disadvantages. These are the software options that are out there right now. And again, we're going to go over some of these on Friday in the lab. So Stata has an entire MI suite of commands that can be used for both multiple imputation, so the actual imputation of the missing values, and subsequent estimation, pooling of the results across these multiple data sets. Okay, so we're going to show examples, and MI impute chain is an example of how you would perform mice within Stata. Okay, so that's an example of the command that you would use to do imputation by chained equations within Stata. In R, we have the MI package that does all this. And the reason we highlight the MI package is going back to Isra's question. MI allows for model diagnostics. Okay, so as part of the imputation process, going through and making sure that you're getting reasonable predictions for each of the variables with missing data as a part of the overall analysis. There's other packages in R like mice and a couple other that do multiple imputation, but there are several that are available. The IVEware software here at Michigan has %impute. So that %impute implements sequential regression or imputation by chained equations. SAS has PROC-MI that does multiple imputation. That's where you can specify a fully conditional specification. And then there's a variety of other packages that do the actual imputation. Solus, M+, there's other tools out there, but these are the predominant ones that we'll be talking about via the lab. Okay. Now, once you create those multiple imputed data sets, then again, you have to combine the results. And in the MI package, Stata offers the MI estimate operator. The nice thing about MI estimate is that you can combine MI estimate with survey capabilities. So you could say, for example, MI estimate SBY logit. And then you'll apply your design-based analysis to each complete data set and pool the results. Okay. So the fact that you can do the imputation and the design-based analysis all in one is a very positive feature here. In R, as part of the MI package, there's a pool function. And that pool function allows you to combine estimates from analyses performed on each of the imputed data sets. Okay. IVEware, we have those additional modules like %describe and %regress that can take the imputed data sets and put everything together. And in SAS, you would combine PROC-MI with PROC-MI analyze to pool all the data sets in the end, or pool all the estimates in the end. So there's always this pair of procedures in each software package, one to do the actual imputation, one to do the combining of the results once you have the complete data sets. And that's what we're going to be illustrating on Friday. Okay. Now, I talked briefly about the fractional hot deck. I know that we're over, but this slide just kind of summarizes the general approach of splitting up the cases into multiple rows to do the actual imputation and splitting the weights. The nice thing about this approach is that it's implemented in SAS in proc survey impute. So if you want to consider this as an alternative for complex sample survey data, you can actually use proc survey impute. And to my knowledge, I think they've been working on an R package that now makes it available. But I'm not positive if that's available on CRAN yet. It might be. But as of right now, it's definitely implemented in proc survey impute as a general strategy. And it generally uses the jackknife for variance estimation as a supplement. Okay, and then the last couple slides here, these are just some of the more popular articles that I've been referring to about these different approaches to different types of statistical analyses with missing data, whether it's imputation, maximum likelihood, etc. If anybody would like to see copies of any of these articles, some of them are already up on Canvas, but if there are any here that aren't already up on Canvas, because some of these are books, just let me know, and I'm happy to let you borrow a book or to share an electronic copy of any of these articles if you'd like to read a little bit more about some of these different approaches. Okay, so again, imputations, there's a vast literature on it. And what we're going to do on Friday in lab is walk through how to carry out a full multiple imputation analysis using the tools that are available within Stata and R. So you can get a flavor of how that works in practice. Okay. So that's what I wanted to cover today about dealing with missing data in surveys. Any general questions right now about the concepts or what we talked about? Any general questions? Yep, Myra?
At the beginning of class, you said talk about matrix sampling.
Yeah.
And that is missing by design.
Right.
And what article talk about this?
Yeah, there's a great article by Grizzle and Raghunathan. I believe the year was 1995. I don't think it's listed here. Yeah, but Grizzle and Raghunathan, they have an article talking about the whole idea of inference based on that kind of matrix sampling, okay, and how you can use multiple imputation to fill in those missing values that are missing by design before making your overall inferences. So that's kind of the seminal article. Yeah, just right about it.
Here's a follow-up on the matrix sampling.
Yep.
Is it similar to the split questionnaire?
It's exactly split questionnaire. It's just another name for split questionnaire. Same thing. Yep. Any other questions? Okay, I think we are all set for today. So again, if you haven't heard back from me yet about the final project drafts, I'm going to do my best to finish those off today. And then in Friday's lab, again, we're going to go over the general approaches to imputation and illustrate some of these tools. So, okay. All right, we'll see everybody on Friday.
Do you need a specific style of references?
No. Okay.
I also
See you guys are.
Yeah, so I think what brought in some kind of confusion is
but I don't know if it's got everything.
when you do just the associations here, you see that for example, for the pregnant women, you see those in the moderate or severe anemia, the kind of proportions are
Oh, yes, that's what I wasn't sure about. So are you saying that among those with moderate to severe anemia, this many are pregnant? Or are you saying it the other way around, where of those who are pregnant, 22.4% have moderate to severe? So it's the latter? Okay.
among those working. You will see, of course, these two not relative, but perhaps here this is lower. In some way, you say that maybe working is a bit protected.
Yeah, but what I don't understand is, how can the number be that large in that cell when both of these are basically between 8 and 7?
But this is different. This is for just break.
And this one is another target.
This is
It strikes me that, that number is so much larger than anything else here in terms of the percentage of the sample that has moderate to severe anemia. So it just seems a little bit off.
okay. Yes. Well, so anyway, if we move here, and this way individual ordered bivariate ordered logistics.
Yeah, but that's what I'm saying. I don't know what that means in the way that the ordinal model is being fitted. Right, because you combine moderate and severe, then there's mild, then there's some category that's not being shown.
Not anemic.
Yeah, so not anemic. So are you modeling, like, I don't know which of these are high or low in terms of the actual valuing. So, you know, if you guys are using Stata, right, Stata's modeling the odds of being in a higher category. I don't know what the values are for these individual categories. Like, I don't know if not anemic is coded 1 or if it's coded 3. Well, that's what I'm saying. It's not clear from this table. So if it were coded 3, that tells me that if you're in that yes group, you have higher odds of being in lower anemia status. See, I don't know that.
So we haven't categorized it whether
Right,
it's multi.
I don't know what the
multi-
value is.
by
So the code, it was.
Yeah, see,
basically-
this says it. This did not. That's all I'm saying. Like, just based on the information in this table, I have no idea what that odds ratio is.
I quoted that they are not anemic because the lowest.
Lower, okay. So then that says that if they are yes pregnant, they have higher odds of being in more severe anemia categories.
Yeah.
But that wasn't clear. That's all I was saying. And that needs to be clarified in the text. But at the same time, though, that also tells you nothing about whether you would fit the ordinal model or the multinomial model that you guys ultimately arrived at. Because these are bivariate analyses, so they're all done in isolation of other variables.
Yeah.
And what you're finding here in terms of these odds ratios doesn't tell you anything about choosing between those two approaches.
Yeah, but we did fit generate the auto fit.
Yeah, I know that, but that was my general comment, is that the process at which you arrived at the multinomial logit model was not clear. So that just needs to be clarified.
Maybe I need to also, maybe, okay, so here we were, okay, so here, I think this, I coded like this. So because it was more, at least it was, this, we were like explaining that if you profit them, they also being higher categories. But we had to record a bit differently. 65. So here, when we're trying to fit the G with GSVY, the geologit, we had to make this one. We had to record differently because just to make not anemic to be a base.
Yeah, I mean, you'd have to do that if you wanted to go the multinomial logit modeling approach. But that would flip all the estimates of your coefficients in the regular logit models that GeoLogit 2 might produce. Right, so I get what you were trying to do to make the multinomial model interpretable, where not anemic was the reference. But if you had support for proportional odds, it would give you the opposite of what you're showing here in this table. That's what I'm saying.
Yeah, but there was no support for that.
Okay, so yeah, so you found that the proportional odds was violated.
Yeah.
Right, so you arrived at that multinomial logit model as the solution. That's what I'm saying, that how you got there just needs to be more clearly described. Because what you said was, I believe if I remember correctly, the parallel lines assumption was violated for I think 3 of the predictors. And then all of a sudden, you were showing the multinomial logit model where every predictor was not allowed to have proportional odds. See what I mean? So your justification was that the assumption was violated for 3, but you chose the extreme route where every single predictor didn't have proportional odds.
Maybe it's just a matter of presentation, because in the tables, if you look at the top and the below, you would virtually see that some of the coefficients are just the same.
I didn't see that. So if you show me your table again, I believe I commented on that. I didn't see that anywhere. I think it was this table. So as I was looking and comparing the odds ratios, nothing was the same. Yeah, that's why I was confused, because above in the text, you say that proportional odds was violated for just 3 of the variables. So I was fully expecting the majority of these odds ratios to be the same,
Yeah, yeah.
but they're not. That was my confusion. Anyway, that was my confusion about trying to understand what you were doing. So the other confusion is that you still called this ordered.
Yeah,
It's
maybe.
not.
So what's the difference when you
This
run?
is nothing different from a multinomial logit model, so you should call it that. It's just a multinomial, that's the other extreme, again, where everything's allowed to vary. That's a multinomial logit model. Calling this an ordered logit model is very misleading. Because it's no longer, it's now a completely generalized logit model, it's no longer ordered. Anyway, but that was my confusion.
Okay, then I think that we'll work on the.
Yeah, you, to support the multinomial logit model you're showing, you'd have to provide evidence that the proportional odds assumption was violated for every predictor. And I wasn't seeing that.
Okay.
Yeah, so see, that's not violated, that's not violated. That's not, that's not, that's not. So far, there's decent support for proportional odds. for
Yeah,
the
there were
cumulative.
only 3, most of them were supported.
Yeah.
Only 3.
Just scroll back over. You might want to
Was fitting it up.
you might want to pause it or something. Anyway, those are the points to sort out that were clear.
I think I might have changed the direction. Yeah.